Well, hey everyone, and welcome back to Stuff in Excel. Sometimes you have data and you need to figure out a model for that data. What's the mathematical model that describes that data, how it's behaving, what direction it's going in, what the parameters are, and Excel can help us do that. So we're going to look at a couple of ways. First, to do a straight line model estimation in Excel, and then second, how to model data that might look like it's curvilinear in nature. We will start off with the most basic kind of cost estimation. And in your early accounting classes, you may have seen something called the high-low method of estimation. So what we have is several months of production levels, and also costs associated with those production levels. So if we plot this data, we'll see what it looks like. I'm simply going to take this data and highlight it, and I'm going to plot it using a scatter graph. So I'll go up here to the top, I'll do insert, and over here under my charts, I'm going to choose this thing that looks like a bunch of dots, and I'm going to choose the scatter graph, and there it is. So this scatter graph, when you look at it, actually sort of looks straight line-ish. We've got a low point of production of 20, a high point of production of 100, and several different production points in between. What we're going to do is draw a line that goes directly between the lowest production point and the highest production point. Now I can demonstrate that line by inserting a line here, and I'm going to start it. I'm going to anchor it here on the 20 unit production level, and we'll go ahead and just pull that down, anchor it right there, and I'll take the other end of this line and we'll anchor it up here at the highest production level. And that is a line that goes through the highest and the lowest point. There's no guarantee that that's the best line through this data. There's no indication of whether or not that line is good, or even if it even captures all the information you need it to capture. I don't know what the slope of that line is. I don't know what the y-intercept of that line is, which means I also don't know the variable cost per unit or the fixed cost associated with this cost function. But I can figure that out. Using the high-low method, we'll simply start here. We'll figure out the maximum amount that is in the range up here. So we'll just highlight that range, hit equals max, and it'll tell me that. Now I'm going to go down, I'm going to pick the minimum amount and highlight that. So I'm actually going to use the XLOOKUP function to look up the cost associated with each of these production levels. So if I do XLOOKUP and Control A to bring up the dialog box, I'm going to look up this value. I'm going to look it up in this array. I want to return the associated value in this array and hit enter, and there it is. And I can do the same thing for my low production, equals XLOOKUP. Control A, I'm looking for this item. I'm looking for it in this array under quantity. I want to return the associated value in the cost column, and there it is. So what I've done is I've figured out my high production and my cost associated with the high production, my low production and the cost associated with the low production. Now, we all remember from our old math courses where we knew and know and remember that y equals mx plus b, where m is the slope of the line, in this case variable cost per unit, x is the amount of production, b is the fixed cost, or the y-intercept on this line. And so essentially we get mx, the slope, by taking the change in y, which is my cost, change in y, over change in x. We used to call that rise over run, if you recall. So I'll simply take my 14,800, my change between these 2 points, divided by the change between the 2 production points, and I get $185 per unit. That's going to be my variable cost per unit. I can't even spell. Now, my total cost, since it was 19,000, is there. I'm going to use the high level. My variable cost is going to be my number of units of production times my variable cost per unit, and that's going to tell me that my fixed cost is $500. Now, we could have also gotten this by starting with the low point. We could have gone, that's 4,200. And that our variable cost is 20 units times $185 per unit, and we still would have gotten $500. So we know this line here has a slope of 185, or variable cost per unit of $185 per unit, and it has a y-intercept of $500. That's my fixed cost for this particular function. So that's helpful, I guess, but like I said, we don't know if that's even the best line. That is a line. It is a measure of distance, or a measure of the line that goes between the low point and the high point, but it doesn't tell me anything about what's going on here in the middle, and it doesn't tell me that I've maximized or found the best line through these data points. So let's go find another way that we might want to do this. The data you see here is the same data that we used for the high-low estimate. I'm going to once again highlight this data and make a plot of it. I am a big fan of plotting the data. Let's see what it looks like before you start trying to model it. Let's see if that data has a straight line feature to it. Is it a curvilinear feature? Does it have fluctuations and patterns in the data that we might want to model? All that will be important and will pop out when you run a picture of the data. So here we see, and the data in this particular example is fairly straight line. As you'll see in the next data, it's not, and that's why you would want to use a different model. So how would we do this? Well, before we do, let's remember what we did earlier. We actually fit a line between the high point and the low point here. So that was the low point right about there, and my high point is going to be right up in here. Now I'm going to make that line orange, and in fact, when I do my next step, that line's going to move, so don't get all panicky. So that's a line, but again, we don't know if that's the best line, the line of best fit through this data. But what we can do is we can actually create that line, and the way we do it first is we click on any one of the data points. So you'll notice when we do, it'll highlight all of the data points. Then we're going to go to one of the data points and right-click on it, and we're going to do a Add Trend Line. See that right here? Add Trend Line. And it's actually going to fit a line to that data. Now again, this data, that orange line moves, so I'll replace it. And you can see how the new blue line is slightly different than the old orange line that we had. And because the blue line is a much better line for this particular data. So let's get rid of the orange line, and I'll show you what I mean. So the first thing we can do with this data is we can, if I can click on it, we'll be in good shape. And I'm just going to go back to Add Trend Line. And what it's going to do for me is it gives me a couple of options. First of all, you notice it defaults to the linear option, but there are other options that could end up being in this data as well. Now, if I go down to the, there's two other things down here at the bottom. I can display the equation, and then I can show the R squared. We'll come back to that in a moment. So when I'm going to take this and I'm going to move this over here. This is the same kind of model we had earlier, but it's for this particular line. Now you remember in the high-low example, we determined that the variable cost per unit was $185. When we find the actual best line through this data, we see that the actual slope or variable cost per unit is $189.88. That is a slightly steeper line. And if you go back and look at the earlier part of this video where I had this and the orange line off at the same time, you will see that the blue line does have a steeper slope than the orange line did. In addition, this model says that the y-intercept, or the fixed cost for this cost structure, is $500, whereas this model says it's $474.04. So the fixed cost is lower, the variable cost is steeper when you get the actual best model. Now, how do I know how good this model is? Well, there's a lot of ways I can tell, and one of the ways I can tell is by, if I can get on the line here. We'll format that trend line. And I'm going to add to this something called an R square. Look over here in the bottom right of your screen. See, I can add an R square. I'm going to add that to this model. And you see it says R square equals 0.9825. Well, that's all fine and dandy, but what is the R square? Well, the R square is a measure of fit for the line. The closer this measure is to 1, the better the line is fitting the data. In this case, we were able to get a 0.9825 fit for our R square, which is really, really good. So this is what we would do if we wanted to model some straight line data for for a particular set of cost figures. Now, what we're going to do next is look at how we do a curvilinear function. This is a different set of data, and this data here will look a little bit different when we plot it. Remember what I said, I always like to plot the data first to see what it looks like. So I'll highlight the data, go to Insert, go over here, I'll do a scatter plot of my data. And you can see this data is clearly not a straight line. Technically, can I put a line on this data? I could. I could put a line from my low point, down here, all the way up to my high point, up here, high production point. But you know what? That doesn't fit that data at all. I can tell that doesn't fit the data. The line should actually be something probably more like that. But it certainly doesn't fit this data. A straight line doesn't. It doesn't model the data very well at all, mainly because the data is not a straight line data. So how would I do this? Well, same as we did before. We're going to click on any one of the data points. We will then right-click on that data point and go to Add Trend Line. Now, it's going to automatically fit a straight line to the data, but that's not what we want. We want to see if we can get a much better fit. And in fact, if I display the equation on this and the R-square, what we're going to see on this data is that it's just not very good data at all. The best that I'm getting right now with a straight line through this data is 0.9046. And the question is, can I do better than that? And the answer is I actually can. So what I'm going to do is I'm going to, we'll go to this again. We'll go back to the trend line. And well, it's not, let me do it here. There it goes. So I'm back on the trend line. And what I'm going to do now is I'm going to try different models. Let's try an exponential model. Well, that actually is a really bad R-square for this data, so we don't want to use it. Let's try logarithmic. Logarithmic, well, that's much better. It's the 0.9267 or some better. I don't know if it's a lot better, but you got to deal with logs, and I'm not sure I really like that model. I could go down and do a polynomial model. Let's try the power model. Again, that one's not very good. It's not terrible. It's 0.9463. It's certainly better than any of the others. You can do a moving average model, which actually doesn't help me a whole lot. Let's go to the polynomial model. Now look at this one. This one got me to 0.9961 with 2 degrees of freedom in it. So I can actually increase this and get to better orders with this particular data, but it doesn't help me much. I could actually get to 0.999, 0.9 if I increase this over here from 2 to say 3 or 4. But this is a pretty good model, and it's much better than the original 0.90 R-squared that we got. So this is just a little exercise to show you how you might use the trend line functions built into Excel to help you to model a set of data. Well, I hope that was helpful to you. I hope you learned something and maybe refreshed your mind someone on modeling. But hopefully it's a new tool you can add to your Excel toolbox. If so, please like the channel, and we'd love to have you subscribe. But we'll see you real soon with another video here on Stuff in Excel.